just to briefly introduce myself, I'm a PhD student, both at UC Berkeley and then in the Redwood Center for Theoretical Neuroscience. So I'm coming from the perspective of computational neuroscience, and it's my first time at this conference. And so it's really exciting to be able to give this talk, and I'm hoping that we can have a lot of really rich and interesting kinds of discussion during this time and throughout all this throughout the conference. So today I'm going to be telling you about this talk on this paper called Computing on Functions Using Randomized Vector Representations. And this is joint work with Paxton Frady, Dennis Kleko, and then Bruno Olshausen and Fritz Sommer. Just as a kind of way of introducing this framework, so there's a lot of questions that might be interesting to us from the perspective of neuromorphic computing. We're presenting a framework for computing over these distributed representations. And there's a lot of different problems we can think about or approach here. So one is machine learning. So how can we build distributed representations that are useful for things like classification tasks, or put things in a distributed format that will be useful. For disentangling certain kinds of representations. We can think about this from the perspective of, similar to as we were thinking from the last talk, factorizable image encodings. So being able to create an image encoding that's not just encoding, for example, pixel location at every possible position, but also is able to be shifted or be transformed in a sensible way in a distributed neural code. And then the last kind of thing is what these kinds of representations or what these kinds of theories for how we can compute over vector spaces has to say or tell us about modeling in neuroscience. So what kind of representations we'll see at the kind of single cell level. And so the talk that I'm going to be presenting today is going to be at a very kind of abstract level in terms of how to think about what these computations could be like in a vector space. I think the key point is how to manipulate and transform these vectors in meaningful ways in the original vector space, such that these correspond to useful transformations and computations over elements in the domain that we wish to represent. And the way and approach that we perform this is by extending work that's known under these terms of vector symbolic architectures or hyperdimensional computing. In this talk, I'll probably be using these terms interchangeably, but they're really referring to the same kind of rich model of computing with random high dimensional vectors. And I'll introduce the basic operations in one slide, but I just want to point out that this is a pretty rapidly emerging field. So this plot on the left is just showing the number of papers by a rough estimate that are being published in this topic specifically in recent years. And then on the right, I just want to show how complex valued vectors in particular, or complex valued vector spaces can be mapped onto spike timing and rhythmic spike patterns. This is this Frady and Sommer 2019 paper. And so I think it provides a kind of linking bridge between principles in computing with high dimensional vectors, and then understanding how those computations can be implemented with kinds of neuromorphic hardware. So I'm not coming at it specifically from the neuromorphic end, or in terms of programming specific applications, but you can think of VSAs as providing a sort of algorithmic framework for, what are the kinds of representations that can be realized with a high dimensional vector, and how can those be transformed for interesting kind of computations? And I hope to kind of walk through the three examples that I had in the beginning. So just as a brief introduction to the kinds of vector symbolic architectures as the paradigm, the primitive element in this framework are these random vectors. So A, B, C can just be symbolic elements within this high dimensional vector space. We have methods for manipulating these vectors. So these would be searching or the superposition operation, which would be a summation of different vectors. We can have a binding operation, which you can think of as roughly performing associations or key value pairs between two different elements. So notice that A plus B is creating something like a set, or an element that or a vector that has high similarity to the original vectors A and B, but A and multiplied by B is forming an association or a new kind of vector or element, which turns out to actually be close to orthogonal or distinct from the representations for A and B. And the last kind of operation that's typically used is this ordering operation, which can typically be implemented as a permutation. And this can be useful for keeping track of sequence information, for example. And we can talk about this further in the discussion if people are interested. But there are many different kinds of implementations of these basic principles in different vector spaces. So it could work with a binary vector space, so with zeros and ones, or with a bipolar vector space of -1 and +1. But also with real and complex value vector spaces. And this is just to show that you can understand the kinds of computations in each of these cases underneath these general principles and these general headings. So one question you might have here, if you've never seen VSAs before, is, okay, why use high dimensional vector spaces, or what's the idea of wanting to work with high dimensions? And one perspective from this is you can think of this in terms of kernels, and in terms of the fact that in a high dimensional vector space, two random vectors are very likely to be close to orthogonal to each other. So one way of generating vectors or symbolic information is to generate vectors that are exactly orthogonal to each other. But in an n-dimensional space, this would only guarantee that you can have n symbols within that space. The approach of a VSA method instead is by randomly generating these vectors. If they're in a high dimensional space, it allows us to say, okay, rather than creating an exact Kronecker delta function where the symbols are identical, or where the inner product between the kernel or between the vector representations is 1 only if they're the same and 0 everywhere else, we can approximate this kernel or the similarity metric by drawing these vectors randomly. And in a high dimensional space, due to the concentration of measure phenomenon, as you can see in this diagram, for a low dimension, there's with high probability a chance that the similarity is far away from 0. But as the dimensionality increases, the chance of having two random vectors be highly similar to each other drops dramatically. So this is the intuition for the typical use of VSA in terms of symbolic kinds of applications. And what this has been used for in the past is because this high dimensional space allows for good kinds of separation, there's a large possibility to represent different kinds of data structures with high dimensional vectors. So for example, one could represent a hash table as a summation or a set of key value bindings. Or a sequence information by binding different position informations where K is some index for different positions. And then this the permutation operation is just keeping track of different positions. And then A, B, and C are different elements. So they're formed essentially in this list structure. What a takeaway from this is that the HD computing framework is able to recapitulate a lot of the traditional data structures that you can generate within a computer science, or the traditional data structures you would find in computer science, but it does so in a way that's dimensionality preserving. So it's all working with these random high dimensional vectors. Of course, this runs into the limit that when you have many vectors together in superposition, or you're trying to merge information into one vector, you'll lose information if you try and pack too much information in. But this is the kind of trade-off that you get when working with this kind of HD computing paradigm versus a paradigm in which you allocate memory that's proportional to the number of items that you would have in a kind of list. So far, this has just been talking, or the past few slides I've been talking about how this can be serving as a paradigm for symbolic computation, but we can generalize this to encoding real values, and we can generalize this to multi-dimensional real valued numbers. But let's just first consider the case we're looking at a scalar. So in addition to the operations we had before, we can define a randomized encoding function that takes some real valued scalar and then maps it to, in general, some complex valued vector. And then we use Z of R to represent, Z would be the particular representation of R within this high dimensional vector space domain. And for reasons that we'll come back to, for reasons we'll come back to and explain further, we want this kind of encoding function to be locality preserving. And what this means is that the inner product between two representations, so between R1 and R2, should only depend, first of all, on their relative difference. So it's a translation invariant representation, so it's translation invariant in terms of its similarity. And then secondly, if the values are close to each other, the inner product between these kernels should be high, and then otherwise, if there's a large distance, it should be relatively low. So we can formalize this intuition further. But the idea is that, if there's only a small change between R1 and R2, that they're mapped to a similar part of the vector space. And the second requirement that we'll impose is that the translation or shifting the argument is computed by binding, which means that if we have a binding of the representation for R1 and then to the representation for R2, this is the same as if we took the representation of R1 plus R2 and then mapped it to this vector space. So this is going to be useful when we're working with that vector space for performing computations without relying back on the original scalars or the original kinds of elements. And next, I just want to highlight some results from functional analysis that we're building off of to show the kind of connection between these vector spaces and theory. So firstly is that these inner product kernels are defining a reproducing kernel Hilbert space, which is going to be useful for us to be representing kinds of functions. And we'll talk about the class of functions that these kinds of representations are able to compute over. And then the second is that the kernel shape, i.e. this K function here is determined they're defined by the Fourier transform of a probability distribution. So on one hand, this tells us what the kernel shape might be in a particular situation, so that we can use it for a particular application. And on the other hand, it says that we are able to use, it says that we can design the particular kernel function that we would like by using choosing our randomized encoding function or function f in a strategic way, and we'll show results for both of those cases. So the main takeaway, or the main theoretical contribution that we're adding, is what we call a vector function architecture, which we use to as a direct allusion to the fact that it extends these methods from vector symbolic architectures in addition to these kernel locality preserving encodings. So suppose we have a function that can be written as a summation of these support points. So in this case, K is our kernel function, or you can think of it as a basis function, where Rk denotes a particular offset, a particular offset of that function. And then alpha K is a particular scaling of the function. We can represent this using a vector, which we denote YF, which is the summation of the representation of this kernel at Rk. So we're using our randomized encoding function to generate these vectors Z. And then the summation and scaling, the summed and scaled versions of these randomized vectors is generating this total function over our space. And here I want to note that there are multiple ways of implementing this VFA framework. We can work with complex valued vectors or real valued vectors, or there's ways of doing it computing with sparse vectors as well. And this framework is general and encompasses all of these different kinds of cases. But an interesting thing and an important takeaway is that when choosing a uniform method of sampling these space vectors, and here I'm putting the theorem, and you can look at the paper for further detail if you're interested, the kernel that you tend to get, that you get by sampling, for example, from a uniform distribution, is this normalized sinc kernel, which is in here traced in blue. So it's sine pi x over pi x with a value of 1 at the limit. So it's intuitively, it's fulfilling the properties of the kernel that you would like, such that when the two vectors are the same, or the two encoded values are the same, it takes a peak at 1, and then there's slowly a decaying envelope over time. And in addition to that, the sinc function has at each of these integer values that are not 0, a value of 0 similarity. So it's preserving, or it's preserving similarity for nearby values between this -1 and 1 range, and then otherwise there's a lower amount of similarity, which allows distinguishing between different kinds of representations. And one reason why the sinc function is useful as a basis function for representing different kinds of functions is that actually through the Whittaker-Shannon interpolation formula, we know that the sinc function is a good basis for representing arbitrary band-limited functions. So in this case, I'm just putting the formula for how, with a set of support points, we can approximate a function, or perform interpolation of a function in terms of these sinc kernels, where nt is denoting a particular shift, t is denoting the scaling or this bandwidth factor, and then xn is the scaling or support point. But these are precisely the kinds of representations we have in this VFA framework, where we also have these kernels that are shifted and that are scaled by a certain amount. So the takeaway, or the general message, is that this kind of representation we're defining is able to represent any kind of band-limited function, provided we have enough support points to approximate it well. And in addition to that, we're able to perform manipulations of these function representations within the original vector space. So we can do things, for example, such as compare the similarity between functions, or take the readout of different functions, or read out the function at a particular point. So performing function evaluation, and these are performed by inner products. And this is leveraging that first point, or the first point that the inner products are defining a kernel between different representations. But then we can use the fact that binding is corresponding to addition in this vector domain to perform function shifting, so shifting over the function by a certain real value, and also to perform convolution between two functions, all within this vector representation. And then lastly, we can compose functions simply by adding together two representations. And this relies on the fact that a vector representation is able to encompass information, not just from multiple symbols, for example, but also between multiple support points. So it's the fact that these vectors are fully distributed and allow for this kind of representation. So now to turn to why this is useful, one application is to perform regression with these sinc kernels. So there have been previous existing methods in the literature for how one could estimate a function from noisy samples using sinc kernels that are weighted and shifted over. We can instead of these sinc kernels, we can replace this with an inner product between two of these base vectors, z, which are encoding particular scalar values. And then, because we can do all of this within superposition, we can actually compress this one term, combining the summation of all these points into one inner product between a particular point and between this encoding. So now what this allows us to do is represent this kind of regression with just one inner product between our model and our encoding of a particular point. And another application of this is for density estimation. We can also take the kernel, for example, a sinc kernel, replace it with an inner product, and then given enough sample points, we can represent our model again with just compact one vector yp, and we can show that actually, as you're increasing the dimensionality of your representation, and if you increase the number of samples, that your representation will become more and more accurate. The method is able to do pretty well and performs a pretty efficient way of approximating these kinds of functions. So another key point is that because the phase distribution of these base vectors is determining what the similarity kernel is, if we didn't want if we can use a similarity kernel that's a sinc function, but if we wanted to have an application with a Gaussian kernel, for example, we can approximate that Gaussian kernel with a phase distribution or a randomized encoding that's drawn from a Gaussian distribution. We can do this not just for one scalar value, but generalize this to a real valued vector. And so in the case of 2 dimensions, we can also generate vectors that are kernel or that are kernels that are periodic. For example, in this case, we have a kernel that's creates a hexagonal period, which is drawn to show perhaps like similarity between these kinds of ideas and ideas from neuroscience, drawing from periodic representations in grid cells, for example. But another application of a periodic representation is that it allows for an efficient wraparound of particular representations. And I'll give an example from images in particular. So we can encode an image as a superposition of different values at different pixel locations. So in this case, we have a letter A. So there's actually a sparse number of pixels that are non-zero in this case. And then we bind that information to a horizontal and to a vertical position. This is a compositional representation. So we're able to then create a scene by adding together multiple letter representations. And we can bind those letter representations to different positions. So this is one with E, P, and F. And then we can translate the whole scene by performing one operation on this entire vector. So we're performing this operation in a distributed manner, and we're no longer constrained to doing it just in terms of integers, in terms of pixels, but we can do it in terms of fractions as well, because it's well defined for real variables. And you can see that in this case, the E is wrapping around 25 pixels to the right, and then 20 pixels down. And then the F is doing the same, but there's actually this wraparound effect. And this is generated by the fact that we can use a periodic kernel as shown before. So the last thing that I would want to mention is what the ties are to neuroscience. And I think there's a lot of interest in understanding what at a population code, or what you can do with a distributed representation, and what are the consequences of working with a population code or working with distributed representations for understanding single cell responses. So this is highlighting work in this conference proceedings in computational neuroscience, where the complex valued vectors were mapped onto specific spike times relative to an animal traversing this 2D arena or environment. And the takeaway is that if you look now at single cell responses within this code, as you might do from neuroscience, you observe not only localized place fields, but also this phase precession effect. So there's a dependence on the spike timing relative to an underlying oscillation as the animal is traversing through a particular place field. So I mentioned this as kind of a start for understanding how these kind of high dimensional coding principles can be used to link both population codes and then also understand kinds of single cell responses. So as a takeaway, I think the contributions are threefold. So firstly, we have this unified framework, both for reasoning about symbols and real values with distributed representations. So it extends these ideas from vector symbolic architectures to encompass not only symbols, but also functions. The second is that these kernel methods in machine learning can now be integrated with these VSA methods by simply forming this vector representation that creates the model, and then using inner products to efficiently evaluate the function at a particular location. And we can talk about how this is extending or related to methods, for example, random Fourier features that are well known in machine learning. And then lastly, and this is current ongoing work in progress, but understanding predictions for neural coding principles and single cell representations, such as in the hippocampus. I hope to understand not just responses of things such as place cells, but also periodic representations of ideas like grid cells and how these are working together to create a unified conception of space or the environment. So thanks so much for your attention, and looking forward to answering your questions.